Are we the cosmic oddballs? If intelligent aliens wrote astronomy textbooks, would our solar system be in Chapter 1 as the standard example, or buried in the appendix under strange edge cases? We grow up with a very calm picture of our cosmic home. 8 planets, 4 small rocky worlds on the inside, 4 huge giants on the outside. Everything spaced out in neat, almost circular orbits around a reassuringly ordinary star. It feels like a template, a pattern the rest of the universe might follow. But while that childhood diagram is burned into our minds, the actual data from modern exoplanet surveys tells a very different story. When we point telescopes like Kepler and TESS at other stars, we do not usually see solar system clones. Instead, we see super-Earths and mini-Neptunes, planets bigger than Earth but smaller than Neptune, crowding close to their stars. We see hot Jupiters, gas giants, whipping around in just a few days. We see tightly packed chains of planets, crammed well inside Mercury's orbit. Our own system has none of that. No super-Earth, no hot Jupiter. No compact chain of worlds hugging the sun. This means that, from an exoplanet astronomer's perspective, our familiar layout already looks suspiciously unusual. In the hunt for alien life, this question suddenly becomes more than trivia. For most of human history, we simply assumed that the solar system was the default setting. The Sun, Earth, and Jupiter were the pattern, and everything out there would be small variations on that theme. Now we have thousands of confirmed planets around other stars, and the pattern looks flipped. Our normal might actually be the outlier. If that is true, how rare are Earth-like conditions? How rare might life itself be? It should be noted that our view of the galaxy is far from complete. We mostly find planets that are large, close in, and easy to detect. Delicate, long-period orbits like Jupiter's or Saturn's are much harder to see, so it's time to find out the truth. Is the universe really telling us that solar system-style architectures are unusual, or are our tools biased, making other systems look wild simply because we are only seeing their most extreme planets? Optimistically speaking, we might just be missing a huge population of quiet, spacious Goldilocks zone systems that look a lot like ours. Or, we might discover that our sun's gentle luminosity, our wide planetary spacing, and our lack of super-Earths are all parts of a rare cosmic recipe. So, let's begin. In this video, we will stack our sun, our planets, and their orbits against the best exoplanet data we have. We will ask whether our solar system is truly cosmic standard issue, or the galaxy's custom build, and by the end, we will see where our home really belongs. Front and center in the textbook, or filed under weird but fascinating. Why our system's weirdnesses actually matters, but why does any of this weirdness actually matter? If our solar system is just one quirky arrangement among countless possibilities, does that change how we think about life in the universe? In the hunt for alien life, the layout of a planetary system is not just background scenery. It is the stage, the lighting, and half the script. If systems like ours are common, with wide, nearly circular orbits and a stable Goldilocks zone, then Earth-like worlds might be almost routine. That would mean temperate planets with long, calm histories could be scattered through the galaxy. But if our architecture is rare, if most systems are chaotic or tightly packed or dominated by migrating giants, then intelligent life might be the exception of the exception. It should be noted that, just a few decades ago, this was all speculation. In 1990, we knew exactly one planetary system, our own. No planets around any other star had been confirmed. Today, thanks to missions like Kepler and TESS, and to precise radial velocity measurements from the ground, we have cataloged thousands of planets in hundreds of systems. This means we can finally compare our home to real data instead of to our imagination. And the comparison has been surprising. Many stars host super-Earths and mini-Neptunes between about 1 and 4 times Earth's size on tight orbits of just a few days. We have none of those. Hot Jupiters, gas giants skimming close to their star, were among the first discoveries, making our own Jupiter, sitting far out on a 12-year orbit, look almost old-fashioned. Compact chains of planets, each one hugging the next in resonant orbits, seem almost ordinary out there. Our system, by contrast, is spacious and relatively calm. But while the exoplanet zoo looks wildly diverse, our view of it is skewed. The easiest planets to find are the big ones and the close-in ones, because they tug hardest on their star or block the most light when they transit. A Jupiter that whips around in 3 days shouts in the data. A small, Earth-sized planet on a 1-year orbit whispers. So it's time to find out the truth. Is the solar system genuinely strange, or are we just mostly blind to its true peers? Astronomers are now trying to build a kind of standard model of planetary systems from this incomplete picture. They simulate disks of gas and dust, let planets form and migrate, and then ask, where does a Sun, Earth, Jupiter configuration land on the spectrum? Are we near the center of the cosmic bell curve, or out on the tail, with the statistical oddities? Optimistically speaking, our weirdness might even be part of what made Earth habitable for so long. But to judge that, we need a control group, real systems that look nothing like ours. And some of the most famous of those, like TRAPPIST-1 and Kepler-11, are about as different from the solar system as it is possible to be, which is exactly where we are heading next. From familiar backyard to alien blueprints. So, if TRAPPIST-1 and Kepler-11 are the wild experiments, where does that leave our own backyard? We grew up treating the solar system as the template, the standard diagram at the front of every astronomy textbook. But in the age of exoplanets, we have to reframe it as just one data point in a much larger sample. One way to build a planetary system, not the way. So, let's begin with the blueprint we know best. Closest to the Sun, we have 4 small rocky planets: Mercury, Venus, Earth, and Mars. Their orbits are relatively circular, laid out in neat, non-crossing paths. Beyond Mars, the asteroid belt forms a kind of ragged border, and then the architecture suddenly scales up. Jupiter and Saturn, the gas giants, and Uranus and Neptune, the ice giants, all live on wide, almost circular orbits, spaced generously apart. Farther out still, we fade into distant icy debris in the Kuiper belt, and the even more remote Oort cloud. Overall, it is a surprisingly spacious and orderly system. This means that, as strange as other systems may look, we keep coming back to this one as our benchmark. We know the masses of our planets with exquisite precision. We have detailed measurements of their compositions, their atmospheres, their moons, even their orbital histories through models like the Grand Tack and NICE scenarios. We can test how stable this architecture is over billions of years. No exoplanet system comes close in terms of raw, high-quality data, but while it is our reference model, it should be noted that it is also conspicuously incomplete compared to what telescopes like Kepler and TESS have revealed. There are no super-Earths here, no planets between Earth and Neptune in size, even though those worlds are the most common type we see elsewhere. There is no hot Jupiter grazing the Sun with a 2- or 3-day orbit, and there is no tightly packed chain of planets all crammed inside Mercury's path, the kind of compact inner system that seems almost routine around other stars. So is our quiet, dynamically cold layout an accident or a clue? In the hunt for alien life, that question matters. Giant planet migration may have cleared out any early super-Earths or prevented them from forming in the first place, leaving a lean inner system where a small, temperate world like Earth could stay habitable for billions of years. Optimistically speaking, our very missing pieces might be part of why we are here to ask these questions. So it's time to find out the truth about how unusual this blueprint really is. Keep this mental map of the solar system in mind, because as we tour TRAPPIST-1, Kepler-11, and other extreme systems, we will keep comparing back to this familiar diagram to see whether we are the oddball or the overlooked norm. Our new cosmic census machines to test that mental map. We need more than a few strange systems. We need a survey of the galaxy. But how do you take a census of planets you cannot see directly, around stars that are just points of light? In the hunt for alien life and alien architectures, the real revolution began with a telescope that did something deceptively simple. NASA's Kepler spacecraft stared, unblinking, at over 150,000 stars for years, watching for tiny, periodic dips in brightness. Every time a planet crossed the face of its star, the light dropped by a fraction of a percent. From that dip and its timing, we could measure the planet's size and the length of its year. This means Kepler did not just find a few dramatic worlds, it measured statistics. It revealed that planets with sizes between Earth and Neptune, so-called super-Earths and mini-Neptunes, are incredibly common, even though our own system has none. It uncovered compact systems where multiple planets orbit closer in than Mercury, tracing tight orbital chains that look nothing like our wide, orderly layout. After Kepler, TESS took over the search, instead of staring at one patch of sky. The Transiting Exoplanet Survey satellite scans almost the entire sky in sectors, focusing on bright, nearby stars. Its planets are easier to follow up from the ground, and that is crucial, because the transit method alone only gives us half the story. We get radius and orbit, but not mass, not density, not whether a world is rocky or wrapped in a thick atmosphere. So, let's begin the second technique. From observatories on Earth, astronomers use radial velocity. They measure the tiny wobble of a star as planets tug it back and forth in their orbit. The motion shifts the star's spectrum through the Doppler effect. By tracking those shifts, we can infer the planet's masses and how stretched or eccentric their orbits are. Transit plus radial velocity turns a dim dip of light into a three-dimensional planetary system. Pattern interrupt. What if we had only used radial velocity first? Then, our early catalog would have been dominated by massive, close-in worlds, and we might have concluded that hot Jupiters were the standard template of the universe. It should be noted that both methods have strong detection biases. They are most sensitive to large planets hugging their star, completing orbits in days. That is why the first wave of discoveries was full of hot Jupiters and tightly packed inner systems. Cooler, more distant planets like Jupiter, Saturn, or an Earth-like world in a wide Goldilocks zone are far harder to see. Yet even with those caveats, the impact was enormous. Before Kepler, we knew only a few dozen exoplanets. After Kepler and TESS, we had thousands, enough data to say what planetary systems usually look like. Optimistically speaking, we expected many solar system lookalikes. Instead, the cosmic census told us something uncomfortable. The universe does not often build exact solar system clones. So it's time to find out the truth about what that verdict means for our own chances, and for systems like TRAPPIST-1 that seem to follow a very different blueprint. Two futures: are we rare or just hard to see? So if the universe does not usually build solar system clones, we are left with a sharp, uncomfortable choice. Are we the strange ones, or are we just looking in the wrong way? Those are really the two futures on the table. Either our solar system is genuinely unusual compared to most planetary systems we have seen, or systems like ours are common, but they are currently invisible to our biased instruments. In the hunt for alien life, that difference matters far more than it might seem at first glance. Let us take the first possibility seriously. Suppose we really are an outlier. Our sun is relatively calm, especially compared with a typical red dwarf that flares violently. Our planets are widely spaced, on nearly circular orbits, with no super-Earths crowding close to the star, and no hot Jupiter skimming the inner regions. This means the exact chain of events that produced Earth's long-lived oceans, a stable atmosphere, and billions of years for complex life to evolve might be a rare cosmic accident, stitched together from low-probability steps. If that is true, then most planetary systems might look more like TRAPPIST-1 or other compact chains that Kepler discovered, where planets huddle close to their star in tight resonances. Many could be baked, tidally locked, or repeatedly disturbed by migrating giants. Life might still appear, but worlds with Earth-like calm might be as unusual as a quiet park in the center of a busy city. But there is a second possibility, and it is just as dramatic. Our tools are not neutral. Transit surveys like Kepler and TESS are exquisitely sensitive to big planets in short orbits because they pass in front of their star frequently and block a lot of light. Radial velocity searches also favor close-in giants that tug strongly on their star. It should be noted that a Jupiter taking 12 years to orbit or an Earth taking 1 year at a comfortable Goldilocks zone distance is much harder to spot and can easily hide in the noise. So maybe we are not rare at all. Maybe distant Jupiter-like orbits and sparse inner systems are quietly common, waiting for longer surveys and more sensitive instruments to reveal them. In that case, the universe could be filled with cosmic suburbs like ours, but we have been peeking through the wrong keyhole, mistaking the bright, crowded downtowns for the whole city. So it's time to find out the truth. Are we living in a quiet neighborhood that almost no one else occupies, or have we simply built telescopes that are blind to our true peers? In the next sections, we will walk through what thousands of exoplanets are already telling us, their sizes, their orbits, their resonant chains, and wild migrations. And we will see which of these futures the data is quietly pointing toward. So, let's begin to read that cosmic census in detail. Welcome to the survey. How we'll judge weird so if the cosmos is holding a census, how do we actually read it without getting lost in the numbers? We need a guide. I am your host for this tour through alien planetary systems. And on this channel, we take the latest space telescope data and turn it into a story about how worlds form, evolve, and maybe even host life. In the hunt for alien life, it is not enough to stare at a single strange planet. We have to compare entire systems and ask where our own fits in. So, let's begin by setting out a clear roadmap. First, we will step back and ask, what is normal out there? We will use the Kepler and TESS surveys, plus decades of radial velocity measurements to sketch the typical planetary system in our galaxy. This means looking at what planet sizes are most common, how tightly they pack around their star, and what kinds of stars they usually orbit. Once we have that baseline, we will zoom in on our own backyard. We will line up Mercury through Neptune against that cosmic average and see where things match and where they do not. Why are there no super-Earths between Earth and Neptune here? Why do our inner planets sit so far from the Sun, compared with many exoplanet systems that cram multiple worlds inside Mercury's orbit? Then we will push further and ask what all of this implies for habitability. Are we living in a rare, just right configuration for long-term stable climates? Or are we simply one example among many different, equally habitable arrangements? It should be noted that we still have huge gaps in the data, but the patterns we do see are already provocative. To make this concrete, we will walk through 4 case studies. TRAPPIST-1, with its 7 Earth-sized planets around a red dwarf, shows us a compact, resonant chain that makes our own orbits look spacious. Kepler-11 and Kepler-90 reveal systems where super-Earths and mini-Neptunes crowd close to their star. HR 8799, with its directly imaged giant planets, looks more like a scaled-up, rearranged version of our outer system. Each one highlights a different architecture the universe seems to prefer. So it's time to find out the truth about how our system compares. We will systematically check off star type, inner planet layout, presence or absence of super-Earths, and whether hot Jupiters or migrating giants have reshaped the real estate near the star. Optimistically speaking, by the end of this journey, you will be able to glance at almost any exoplanet diagram and immediately see where our solar system is normal, where it is odd, and why that might matter for life. And next, we start with what the surveys say is typical in the galaxy. What counts as a normal planetary system now? So, if we want to know whether our solar system is strange, we first have to ask a deceptively simple question. What does a normal planetary system even look like? Because our childhood diagram of neat, widely spaced orbits is not the baseline the universe seems to prefer. Over the last decade, missions like Kepler and TESS have given us something we never had before: statistics. Instead of one example, we now have thousands. This means we can talk about distributions, not anecdotes. How big are most planets? How close do they typically orbit their star? Which kinds of stars host most of the known worlds? In the hunt for alien life, these numbers are our new cosmic census. When we plot planet size from these surveys, one result jumps out. The most common type of planet we see around Sun-like stars is not an Earth twin and not a Jupiter. It is a class we do not have at all: super-Earths and mini-Neptunes, roughly 1.5 to 4 times Earth's radius. Many of them huddle close to their star, with orbital periods of only a few days to a few weeks. It should be noted that, from the galaxy's point of view, our lack of a single planet in this range is what looks unusual. But why is that? To answer, we have to separate star factors from planet factors. The mass and type of the star set the overall energy budget, the width and distance of the Goldilocks zone, and the radiation environment that any atmosphere must survive in. A small red dwarf bakes its planets up close with flares. A larger sun-like star spreads its warmth farther out, so the star shapes the stage. Planet formation and migration, on the other hand, arrange the cast. Disks of gas and dust build rocky cores, grow giant planets, and then gravitational nudges move those worlds inward or outward. That sculpting process decides whether a system ends up with hot Jupiters skimming the star, super-Earths packed inside Mercury's orbit, or a wide, relatively calm layout like ours. So, let's begin to compare not just individual planets, but whole architectures. One of the biggest surprises from Kepler is how many systems are incredibly compact. We now see multiple planets all orbiting well inside where Mercury is in our system, often locked into resonant chains where their orbital periods follow simple ratios like 3:2 or 2:1. TRAPPIST-1 is an extreme example, but it is not alone. Compact multi-planet systems are not rare oddities, they are a common outcome of planet formation. So it's time to find out the truth. If compact chains and super-Earths are normal, where does that leave a system with no close-in planets and a big Jupiter far away? Next, we turn to the stars themselves and ask what kinds of stars are actually hosting most of these worlds, and how does our sun stack up? Our sun versus their suns, setting the stage if we want to know whether our solar system is weird. We have to start with the star that built it. What kind of cosmic engine is the sun, and how does it compare to the stars that host most of the planets we have found so far? So, let's begin with the basics. Our sun is a G-type main sequence star, about 1 solar mass by definition, with a relatively steady luminosity and a total lifespan of roughly 10 billion million years. It is 4.6 billion years old, which means it is almost exactly middle-aged. This stability is not just a fun fact, it sets the long, calm stage on which Earth, and potentially life, can slowly evolve. But while the Sun feels standard to us, it should be noted that it is not what the galaxy mostly makes. Most stars out there are smaller, cooler M-dwarfs, the red dwarfs. They can burn for hundreds of billions of years, far longer than a G-type star, and they dominate our stellar neighborhood. Proxima Centauri, our closest stellar neighbor, is a red dwarf, as are the majority of nearby stars we have cataloged. This means that many of the most famous compact exoplanet systems, including TRAPPIST-1, orbit these tiny, cool stars. Their planets circle so close in that a whole system can fit well inside the orbit of Mercury. A year can last only a few days. In the hunt for alien life, that makes red dwarfs deeply attractive targets, simply because there are so many of them, and their planets are easier to detect. However, the type of star does something crucial. It reshapes where the Goldilocks zone sits. Around a red dwarf, the habitable region where liquid water could exist is tucked in tight, very close to the star. Planets there whip around quickly, often ending up tidally locked, with one side in perpetual day and the other in endless night. They are also much more exposed to stellar flares and high-energy radiation, which can strip atmospheres or sterilize surfaces. Our Sun, by contrast, pushes its habitable zone farther out, giving Earth a one-year orbit and a comfortable distance from most violent space weather. Optimistically speaking, that gentle environment may help atmospheres survive and climates stabilize. Here is the pattern interrupt. The Sun itself is only mildly unusual. Its mass and type are somewhat less common than red dwarfs, but not extreme. What really stands out is what the Sun's calm middleweight nature has allowed our planetary system to look like. Our planets follow wide, nearly circular, well-aligned orbits. Many exoplanet systems, especially around other stars, show eccentric, elongated paths and tilted orbital planes, with planets packed close to their star or jostling in resonant chains. So it's time to find out the truth. Maybe the real oddity is not the Sun alone, but the combination of this particular star with this unusually orderly planetary architecture. Next, we will ask how such a layout might have formed, and whether that quiet structure is a hidden advantage for life or just one strange outcome among many. The exoplanet revolution, what we actually found. So, if our solar system might be the quiet oddball, what does a normal planetary system actually look like? Because once Kepler and other surveys started staring at thousands of stars, the picture that emerged was not what most of us grew up with in school. In the hunt for alien life, Kepler's first big revelation was simple and profound. Most Sun-like stars have planets, not just a few. The majority. But while we might expect a lot of Earth copies and distant Jupiters, the most common worlds in the data were something else entirely. We found super-Earths and mini-Neptunes, planets between about 1 and 4 times Earth size, with masses up to 10 times higher. These are planets with thick atmospheres, deep envelopes of gas or water, or something in between. They are big enough to be very different from Earth, but too small to be true gas giants. And our own system has none of them, not one. It should be noted that this missing middle is one of the clearest signs that our layout is not the galaxy's default option. Then there's where these planets live. Many systems Kepler saw pack multiple planets extremely close to their star. We are talking orbits of a few days, maybe a couple of weeks, a year that lasts less than your summer vacation. Compared to that, Mercury's 88-day orbit looks like a distant, slow-moving outpost on the edge of nowhere. Some systems line up 3, 4, even 5 planets, all inside the orbit of Mercury, forming tightly packed inner systems that almost look like the rings of Saturn, only made of worlds. This means that, for a typical Sun-like star, the real action is huddled right up against the stellar furnace. And then, we have the hot Jupiters. These are Jupiter-mass planets whipping around their star in just a few days. They are rare overall, but still easier to find than a Jupiter twin on a wide, circular orbit like ours. Statistically, it is more common to see a giant planet that has migrated inward and parked itself close to the star than one sitting calmly 5 astronomical units out. Optimistically speaking, our own Jupiter may be a bit unusual. The orbital patterns are different too. Many exoplanet systems show planets in or near resonances, where their orbital periods lock into neat ratios, and their paths are often more elongated and tilted. Their architectures look dynamically excited, full of past gravitational tussles, compared to our relatively calm, circular orbits. So, let's begin to accept an unsettling implication. If you randomly picked a planetary system from the Kepler catalog, it would almost certainly not look like our wide, orderly layout of small inner worlds and distant giants. So it's time to find out the truth. How did we escape the crowd, and what chain of events carved out this strange, seemingly empty inner space around our star? Why are we missing super-Earths and hot Jupiters? So if our solar system escaped the crowd, what exactly is it missing? Because when we look at the Kepler and test data, one thing jumps out immediately. The most common planets out there are super-Earths and mini-Neptunes, worlds between about 1 and 4 times Earth's size. Yet in our system, we leap straight from Earth to Neptune, with nothing in between. No super-Earths, no mini-Neptunes, just a gap. This means something dramatic probably happened early on. Around many stars, we see compact chains of these planets, packed closer in than Mercury, some brushing the edge of the star's atmosphere. Others host hot Jupiters, giant planets whipping around in just a few days. Our own Jupiter, by contrast, sits far out at 5 astronomical units, with no hot Jupiter cousin hugging the sun. Why is our layout so stretched, and frankly empty on the inside? One leading idea is called the Grand Tack model. Picture Jupiter forming first, then slowly spiraling inward through the gas disk, pulled by its own gravitational wake. It should be noted that this inward march may have carried Jupiter to roughly the current orbit of Mars, bulldozing and stirring the material that might have built close-in super-Earths. Then, Saturn formed and joined the dance. Once Saturn grew massive enough, the two giants locked into a gravitational resonance and reversed course. Like a sailboat tacking in the wind. Together, they migrated back outward. In the hunt for alien life, this kind of giant planet migration is a key theme because it can completely rearrange where habitable, Earth-like planets are allowed to survive. As Jupiter plowed in and then back out, it could have shattered large embryonic planets, scattered them into the sun, or ejected them from the system entirely. Instead of a row of massive inner worlds, we were left with a thin, low-mass disk that eventually assembled into Mercury, Venus, Earth, and Mars. No super-Earths, no hot Jupiter, just a modest set of rocky planets with relatively calm, circular orbits. But the story does not end there. The nice model adds a second act, hundreds of millions of years later. In this scenario, the giant planets, Jupiter, Saturn, Uranus, and Neptune, undergo a delayed instability, reshuffling their orbits. As they scatter leftover planetesimals, they sculpt the Kuiper belt, stir comets, and help define the asteroid belt we see today. Our inner region ends up dynamically cold, few massive bodies, mostly stable paths. Optimistically speaking, that gravitational ballet might have cleared out threats and set the stage for a long-lived, habitable Earth. But did this chaos actually make early planets suffer first? So it's time to find out the truth. Did Jupiter's wild journey nearly erase our chances for life, or quietly make them possible? Compact clockwork, TRAPPIST-1, Kepler-11, and friends of Jupiter's rampage helped clear our skies. Then what does a planetary system look like when that kind of cleanup never really happens? Because out there, nature seems to prefer something very different from our wide, quiet layout. So, let's begin with the poster child for compact clockwork, TRAPPIST-1. This ultra-cool red dwarf is only slightly larger than Jupiter, yet it hosts 7 Earth-sized planets, all squeezed into an orbit smaller than Mercury's path around our Sun. A year on the innermost planet is about a day and a half. Even the outermost one loops the star in just over 2 weeks. The whole system is a stack of worlds pressed right up against their star. But it is not just tight, it is synchronized. Many of the TRAPPIST-1 planets sit in a resonant chain where their orbital periods follow simple ratios. When one planet completes a set number of orbits, its neighbors complete their own matching sets, like gears in a watch. This means their gravitational tugs line up regularly, keeping the pattern locked in. In the hunt for alien life, this kind of long-lived stability around a common red dwarf is incredibly tempting. Now compare that to our inner solar system. Mercury, Venus, Earth, and Mars are separated by much wider gaps, and none of them form such a neat resonant ladder. Our orbits are almost politely spaced, dynamically relaxed, with fewer close encounters and no obvious chain linking one year to the next. It should be noted that this calm structure is not what Kepler and TESS usually see. Take Kepler-11. This sun-like star hosts at least 6 planets, 5 of them packed inside the orbit of Mercury. Their years range from about 10 days to under 50. Or Kepler-90, another sun-like star with 8 known planets. Most of its worlds also huddle close in, including a hot Earth-sized planet that orbits in just over a week. These systems tell us that compact inner architectures are not just a red dwarf quirk, they are common even around stars, much like our own. Quick pattern interrupt. Imagine standing on a TRAPPIST-1 world. In the twilight sky, neighboring planets loom many times larger than our moon, racing through phases in a matter of hours. Eclipses are frequent, and your year might be shorter than a long weekend. Then we snap back to Earth, where the nearest planet is a bright dot, and seasons crawl by slowly. This contrast matters. Exoplanet data suggests that forming many close-in planets is easy for the universe, ending up with a sparse inner system like ours, with no super-Earths and no hot Jupiters, may require special circumstances. So it's time to find out the truth. Did our strange, stretched-out architecture quietly tilt the odds for a long-lived, habitable Earth-like world, or are we just one weird example among countless cosmic experiments? Calm orbits, quiet giant, our system's hidden quirks, if our layout is strange? What about the way our planets actually move? Because when we zoom in on the orbits themselves, our solar system looks even more suspiciously calm. Most of the giant exoplanets we have found do not glide around their stars on neat, circular tracks. Their paths are stretched, like cosmic ellipses pulled tight, and many are tilted well above or below the equatorial plane of their system. But while those alien giants charge along elongated, inclined orbits, Jupiter, Saturn, Uranus, and Neptune trace paths that are almost perfect circles, all lying in a thin, flat disk. This means their distance from the Sun hardly changes over a year, and they rarely stray far from one another's orbital plane. It should be noted that this dynamically cold behavior is not what early exoplanet data led us to expect. Hot Jupiters, eccentric giants, and misaligned orbits made it look as if chaos was the rule. Our giants, especially Jupiter, seemed almost boring by comparison, but boring, in this case, may be a feature rather than a bug. Take Jupiter. Its mass dominates the planetary part of our system, yet it sits far out beyond the Goldilocks zone in a wide, nearly circular orbit of about 12 Earth years. In the hunt for alien life, that placement may be crucial. A giant planet on a tight, eccentric path can fling comets and asteroids inward like gravitational shrapnel. Jupiter, by contrast, often does the opposite. Its gravity can deflect dangerous objects away from the inner planets or capture them into safer orbits, as with the Trojan asteroids that share its path. So, is Jupiter our bodyguard? Optimistically speaking, it might be, but the truth is more nuanced. Simulations show that Jupiter can also send material inward under some conditions. Even so, compared to a close-in, wildly eccentric giant, a distant, nearly circular Jupiter looks far more compatible with long-term stability for any habitable Earth-like world. Then there is the spacing. The planets in our solar system are spread out, with large gaps between their orbits. This wide spacing, combined with low eccentricities, reduces the chance of close gravitational encounters that could yank a planet out of the Goldilocks zone or trigger a cascade of orbital chaos. Over billions of years, that kind of stability is exactly what you want if you are trying to maintain a relatively steady climate and a persistent atmosphere on Earth. Yet when we look outward, many systems tell a different story. We see evidence of past violence, giant planets scattered onto eccentric orbits, missing inner planets that may have been swallowed by the star, and compact chains that look one nudge away from disaster. So, let's begin to ask a slightly uncomfortable question. Are we living in a system that is unusually quiet and dynamically dull, and was that very dullness the silent ingredient that gave complex life the time it needed to emerge? Because if so, then our next step is clear. We have to ask how often the universe builds star systems this calm at all. Can we trust the data? Bias, blind spots, and updates. But before we declare our solar system uniquely calm or catastrophically weird, we have to ask something much less glamorous. Can we even trust our current picture of other planetary systems? Evaluating a star system for normality sounds simple. We compare our planets, our orbits, our giant worlds to what we see elsewhere. But while that feels straightforward, the data we actually have are heavily biased. Most of our discoveries come from two main techniques: watching a planet transit or pass in front of its star, and tracking the tiny wobble a star shows as planets tug on it. Both methods are fantastic, but they are also very picky. Transit surveys like Kepler and TESS are naturally drawn to big planets that hug their stars tightly. A large world closes in, blocks more light, and passes in front of the star again and again, so it leaps out of the data. This means our catalogs are full of hot Jupiters, super-Earths, and compact chains of planets, while distant, Earth-like or Jupiter-like orbits are far harder to spot. It should be noted that if we observed our own sun from far away with a Kepler-like mission, we might only see Jupiter, or maybe nothing at all. Radial velocity surveys have their own bias. A massive planet on a fast, close orbit makes its star wobble strongly and frequently, so we confirm it quickly. A giant planet like our Jupiter, taking 12 years to complete one orbit, leaves a much slower, more subtle signature. In the hunt for alien life and solar system twins, that is a serious problem. Long-period planets require many years, sometimes decades, of patient observation to be nailed down. This means that wide, calm systems with planets spread out on nearly circular orbits are systematically underrepresented right now. They may be there in large numbers, but our current time baseline has simply not caught up with them. Optimistically speaking, the universe could be hiding many Sun, Earth, Jupiter arrangements just beyond our detection threshold. To compensate, astronomers build statistical models that correct for these biases. They ask, given what our instruments can and cannot see, how many solar system-like architectures are probably out there? The answers suggest that such systems are not dominant, but also not impossibly rare. However, these are not direct counts. They are educated reconstructions, with error bars and assumptions baked in. So, at this point in time, with the instruments and baselines we actually have, our solar system does look unusual in several ways. Fewer close-in planets. No super-Earths. A giant planet on a wide, nearly circular orbit. So it's time to find out the truth with better tools. Future missions like Plato, the Roman Space Telescope, and ever more precise radial velocity campaigns will push us to longer periods and smaller signals, steadily filling in the blind spots. As we weigh our weird or not verdict, we will lean on the best available data. But we will also clearly mark where we are extrapolating beyond what we can directly see. And the real twist is this: even if the statistics eventually say our architecture is rare, does rare automatically mean special or something more unsettling? So, is our solar system the weird one? So it's time to find out the truth. If we step back from all the individual discoveries and just look at the pattern, where does our own planetary system actually sit in the cosmic crowd? We have to recap what really stands out. Most of the systems Kepler and TESS revealed are crammed with super-Earths and mini-Neptunes, planets between Earth and Neptune in size, often huddled close to their star. Many also host hot Jupiters, giant planets whipping around in just a few days. Our solar system has neither. Instead, our inner planets are small, widely spaced, and our one true giant, Jupiter, lives far out on a broad, almost circular orbit. Each of those traits exists elsewhere. We do see calm orbits, we do see wide orbit giants, we do see systems without hot Jupiters. But while those features appear one by one in the exoplanet data, they rarely show up all together in a single, tidy architecture like ours. This means, statistically, we are drifting toward the unusual side of the distribution. Are we a 1 in a billion freak? Probably not. But are we the median, textbook planetary system an alien student might learn about in school? Also no. It should be noted that our combination of low eccentricity orbits, a relatively quiet sun, and a Jupiter that seems to have migrated only modestly already puts us in a minority class among known systems. Why does that matter in the hunt for alien life? Because those weird features may have made our Goldilocks zone remarkably stable for billions of years. A giant planet that did not plunge inward as a hot Jupiter could mean fewer catastrophic rearrangements of the inner system. Nearly circular orbits keep Earth's energy input from the sun steady, reducing extreme climate swings. The lack of super-Earth sweeping close to the star might have prevented our rocky planets from being scattered, stripped, or drowned in thick envelopes. Optimistically speaking, our odd architecture may have gently protected the early Earth, letting oceans, continents, and a complex atmosphere develop without constant planetary scale resets. But here is the pattern interrupt. A rare layout does not automatically mean rare life. Compact systems around a red dwarf with tidally locked planets and intense stellar activity could still host habitable worlds, just under very different conditions. A TRAPPIST-1-like system might build life in deep oceans, beneath thick clouds, or under protective magnetic fields. In other words, our path to habitability is only one example, not the blueprint. So, let's begin to shift the question. Instead of asking whether the universe is built like our backyard, we may need to accept that we live in a somewhat custom neighborhood. And that is exactly what makes every new system we study so revealing, because each one shows us another way that planets, and perhaps life, can emerge. Your turn in the cosmic survey, because each one shows us another way that planets, and perhaps life, can emerge. So where does that leave us here in our slightly custom neighborhood? We started with a big existential question. Is our solar system normal, or are we the weird ones in the wider universe? In the hunt for alien life, that is not just trivia. It shapes how we read every new light curve, every new spectrum, every new hint of an atmosphere. We followed the data from the first surprise hot Jupiters through compact chains of super-Earths hugging their stars, to migration models where giant planets roam inward and then retreat. This means that what we grew up with in school diagrams, a wide, calm system with small rocky worlds inside and cold giants outside, is not the default setting. It should be noted that, in several important ways, our solar system really does look like a bit of a cosmic oddball. But, while that might sound flattering, it does not make us magically special. Our story is one branch on a very large cosmic tree. Optimistically speaking, that is actually more beautiful. It means there are many different paths to habitable worlds. Our quiet orbits, our lack of super-Earths, our single Earth-like planet in the Goldilocks zone are not the only recipe the universe can use. So here is a thought experiment to end on. Imagine an alien astronomer circling a red dwarf in a tightly packed system, looking back at us. How would they file our star and planets in their catalogs? As an exotic outlier with strangely empty inner orbits? As a boring, spread-out system with only one world in the comfortable zone? Or as something in between, just another data point in their own grand survey? Where would you place us on that scale? If you could trade our calm, spacious layout for a dramatic sky filled with nearby planets, huge crescents hanging above the horizon, eclipses every few days, would you do it? Or do you prefer the long, slow clockwork of our current orbits, even if it makes our skies look a little plain compared to a TRAPPIST-1 style system? Tell us in the comments which exoplanet system fascinates you the most, and why. Is it a compact chain around a red dwarf, a hot Jupiter grazing its star, or something that looks almost but not quite like home? And would you actually want to live there, under that alien sky? So it's time to find out the truth about how ordinary or extraordinary our own system really is. And that story is still being written. If you want to follow the next chapters, deep dives into specific exoplanet systems, new missions, and fresh JEST results, make sure you subscribe or follow so you do not miss what we discover next about our place in the universe.